Okay, so in this video we're going to look at finding for a circuit Z equivalent. And remember here that we mentioned it in the previous lesson, impedances add, I should say, instead of saying add, combine in series and parallel, just like resistors. And again, the reason for that is that my equation here is that I have V is equal to Z times I, so it's Ohm's law. So it makes sense that impedances would combine together just like resistors. So let's look at an example here. Okay, so I've got several things here. Now what you'll notice here in this problem is that the impedances are already labeled. So we're not having to do any kind of conversions here. They've already done, the conversion. So what this means is we actually have no idea what frequency the circuit is seeing. But we've already put the impedances, they've done all the computations for us. And then this is 13.6 ohms. So then we just go ahead and combine these like we would normally. But what I'm going to do here first is notice that if I look at just what's inside this box here, I'm going to just redraw that here. I'm going to have a 6 ohm resistor and a minus J2 ohm capacitor. But what we can do, those are in series. Now when I combine them together, they're not like a component anymore. It's a combination of components. So we typically just write a box and we do 6 minus J2 ohms. And the reason we do that is because that's now combined together and it's a single circuit element. Now it's not a resistor or capacitor, it's a combination of those. But it lets us look at the circuit a little bit easier. And I'm going to do the same thing for these components right here. And so I would have J12 and a 4 ohm, and that's just going to go to, well, 4 plus J12 inside a box, and then the lines on there. So I'm going to redraw my circuit here. What I'm going to do is I'm going to redraw it here, and I'm going to have my capacitor still at negative J12.8. But now I'm going to have this box here of 6 minus J2, and I'm just going to put that in a box. And then I have another one that is 4 plus J12. Put that in a box. Still got my 13.6 ohm resistor. And then my 5 ohm resistor. And my, whoops, that's not a capacitor, it's an inductor. J10 ohm inductor. Let me just double check to make sure. Yep. That's correct. Now what we should notice here is if I look at this right here, these are all in parallel. Now if you're in parallel, remember these impedances behave just as resistors. So if you're in parallel, you would do 1 over Z1 plus 1 over Z2 plus dot 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 1 over Zn to the negative 1. And then we also have, just like we had for resistors, if you have 2 in parallel, instead of doing the 1 overs, you could do Z1 times Z2 over Z1 plus Z2. Alright, so we're going to combine those all in parallel now. And so if I combine those all in parallel, what would I get here? Well, I'm going to have Z is equal to 1 over 6 minus J2 plus 1 over 4 plus J12 plus 1 over 5 plus 1 over J10. Now, and then this is all to the negative 1 power. Now I want to take a moment here and look at this one here. I see so many people entering this in their calculator incorrectly. I see people writing this in their calculator as 1 over with the division symbol like this, or actually, or I see them doing 1 divided by 10i. And both of those are incorrect because you need to make sure to put parentheses. So what you need to do, and I'll put it in blue, put parentheses around these, because most calculators out there would interpret this as 1 divided by 10, which is 0.1 times I. So you'd get 0.1 I from that. And in this case, you'd get 1 divided by I, which is negative I, and then times 10, so this would be negative 10i. So you need to make sure when you do those divisions that you're a little bit careful on your work using your calculator. You don't want to lose points for calculator errors. And the end result we get then is that Z is equal to 2.4 plus J 0.8 ohms. Now let's redraw the circuit to see where we're at here. We have my negative J 12.8 and a box here. 2.4 plus J 0.8, and then my resistor, which is 13.6 ohms. And then again, if I combine all of those together, that's on series now, so my final thing for Z equivalent, I'm not going to actually show the addition. I mean, these are easy things to add up. We would wind up with 16 minus J 12 ohms. So that is definitely my equivalent impedance. You could put it in polar form if you wanted to. There's not a need to do that, but if we did, I'm just doing it real quickly on my calculator. This would be equal to 20 at an angle of 36.87 degrees. I'm sorry, negative 36.87 degrees if you put it in polar. But actually rectangular is preferable to leave it as, but if you want to do the circuit here, draw the circuit. Here I'm going to show you, don't draw. Just 16 minus J 12 ohm. In a box. Don't draw this. Well, if I'm saying don't draw this, what should we draw? Well, let's look here at Z equivalent again as 16 minus J12. Well, with our impedances, we know that the real portion, the only thing that can be real, is a resistor. And then the imaginary portion, this is either a capacitor or inductor. But then here, this negative sign tells me which one it is. Gives capacitor. Because remember, if you look at our equations for impedance, I'm going to scroll all the way back here, way back. equations for impedance here. ZL is a positive j omega L, so it's always going to be positive j. Z capacitor is minus j over omega C, so it's always going to be a minus j. So if you see minus j, that's always some kind of capacitive effect, and if you see plus j, that's some kind of inductive effect. So if we wanted to draw the circuit we would actually draw would be a 16 ohm resistor followed by capacitor. Now you could flip the order of the capacitor and resistor, it doesn't matter, but I typically just draw the resistor first and then minus j 12 ohm capacitor. So this would be the circuit you would draw for ZEQ.